Visible now?
Yes, sir.
Yes, sir.
Okay. Okay. So maybe I should start again. So this is just copied from the live IGL tutorial. Okay. I'm just reading these two meshes, CAT0H2 and CAT0. CAT0 is this particular mesh that you can see over here. And the CAT0H2 is unfortunately the head of this CAT. I played around with MeshLab yesterday and was able to extract this part of the mesh. All right, and it's not just per se, it's of course the head of the CAT in this mesh, but I've also sort of artificially rotated it and translated it so that ICP, using ICP makes sense. Okay. If you wish, you can add sort of noise to the vertex positions of this particular mesh just to experiment more. Then let me just quickly, this is what basically you are supposed to write. Okay, this main ICP algorithm. You go through this. This find core is a function that I have written and is shared with all of you. Basically looks for computes the distance of every point of one mesh to every point of the other mesh, and then finds the one, returns the indices for the one which has the smallest distance. That's what it does. Okay, so this function is already given to you. Second function that is also given to you is myRigidAlign. So basically it takes the two, so one mesh and the vertices in the other mesh which are put in a corresponding order to the first mesh. Okay, so that is the input, and then basically it finds the best optimal rigid transformation. Okay, as you see it at SVD as discussed in the morning, and then also does apply these rigid transformations that you have just found out on the set of points X. Okay, so remember in this myRigidAlign function, it aligns the set X to the set of points in Y, not the other way around. Okay, please be careful. These two functions are already given. Basically, you have to write the main myICP function. I've also described the steps in some details in the notebook shared with you. Let me just run and display the results. Okay, I didn't run this. Once again, I claim my functions that I've written are not necessarily optimal due to Python. You see, these list of numbers is the least square error, right? And you can see that it's sort of going down monotonically. This can be proved theoretically, right? That the least square function, least square error will always go down monotonically. It will converge to a local minimum. Let me show you the results. Right, I hope you can see something. This is the original mesh. These red point sets are the vertices of the CAT0H2 mesh. Okay, so they're not, as I said, it's a slightly rotated and translated version of this. And these blue points that you can see are basically the result of rigid ICP. So as you can expect, since these red points are near the actual set of points from where they were picked up, so the rigid ICP will converge. You can also maybe take this as an exercise to rotate and translate these red points to a different place from where it will not converge to the right set of points. And I think you can find thousands of such examples. If, for example, if you put it near the tail, there's no way it will sort of converge to the right area. Is that fine? Any doubts here? I'm not able to show you. Okay, maybe of cells. Right, so this is again similar to the example shown in these slides. Let's go ahead. So this was rigid. Next is non-rigid shape alignment. Okay, so first method we saw in the morning session is this SVD-based method. Again, this is something you're supposed to fill in. I'm not going to discuss this. It's just 4-5 lines you can see. And then again, let's run. Okay, so here there's one thing you need the distance between all pairs of points in the two meshes. That's going to take a long time to compute. By the way, there's also an IGL inbuilt function that computes geodesic distances between points. So I just used it and I've computed the distance matrices for both these meshes. There are these two meshes, CAT0 and CAT4. These two meshes are the same two meshes that we saw in the slides in the morning. Okay, so it's nothing new. And both these distance matrices have been shared with you. I hope you can access them. Okay, so let's just run them. This piece of code. And so again, as I said, my codes are not optimal, and specifically what I want to say over here is, remember this SVD based method computes the SVD of that minus half JDJ matrix. That JDJ matrix is n by n. In this case, both these meshes, CAT0 and CAT4, both of them have 3400 vertices, which means that B is a matrix of size 3400 by 34. Now again, I want to compute an MDS, an embedding of these set of points. I need to compute only the first three singular vectors and three singular values. Now, I am not familiar with what command gives you only the first three singular vectors. So I've just used the entire SVD, okay, and which is why it's still taking a lot of time. It's 3400 singular vectors and singular values over two meshes. That's going to take some time. Right? But if you are familiar with the Python function that computes, let's say, any first k singular vectors and singular values, then you should use that. Is anyone familiar with such a function?
Sir, this matrix JDJ matrix is a symmetric matrix, right?
Yes.
So SVD is the same as the eigen decomposition.
Yes.
So
Apart
we can,
from, there's just one small difference. I think the eigenvalues you have to consider as absolute values.
okay.
That apart from that, yes, there is no difference.
Yeah,
So,
so
okay. Mhm.
so there is a method that if we want to find only first three
Okay.
eigenvector which have three eigenvalue, highest eigenvalue. Yes.
Okay. Right. So then in your implementation, you should probably use that because
Okay.
it is given the results, but of course, we are just wasting computations by computing all 3400 singular vectors, which are not going to be used anyhow. Anyway, so let me first show you the source meshes here. This is a usual CAT0 mesh, and seen in the morning session, this is your CAT4 mesh. Okay. And now let's see the output of the SVD based MDS method for both meshes. Okay, so V0S is the MDS obtained for this particular mesh, and V4S is the output of MDS obtained for this mesh. So sort of still roughly recognize the cat shape. Of course, I mean, not per se. You sort of see that these were the legs, this is the tail. Still sort of roughly spot the eyes here. These two depressions are the eyes. What's happening is you're sort of essentially stretching out or straightening out the mesh as far as possible. And by no means I'm saying that the SVD method is the best, but you roughly get to see what it is doing. It's sort of converting things into flat spaces as much as possible. Right? And this is the first one, and this is the second. Again, I mean, there's very little resemblance with the original cat mesh, but again, you can spot the eyes, the four limbs, and the tail. More importantly, of course, remember the idea is not to preserve the cat shape. The idea is to preserve the distances, and out of which you should be able to do a rigid comparison between this and this. Do not know how to sort of plot both these surface meshes in the same figure in Python. Excuse me for that. I don't. Does anybody know how to plot both these meshes on the same figure? Otherwise, you'll have to sort of just look at both of these. So while rigid alignment may now be possible, but of course you can see that all vertices on the limbs and on the face are now sort of collapsed into a very small region, and it's going to create a lot of issues. There's very little structure left. So again, the conclusion is yes, SVD method does compute an MDS, but not necessarily the best one. Okay, so with that, let's move for the last demo of this session. So there is this SMACOF algorithm. SMACOF is an acronym that stands for, I think, scaling by minimizing a convex function. Okay, I did not really get into the details of the optimization algorithm, and I don't intend to unless some of you sort of push me to do it. Okay, so let me just run this. Again, this is an iterative process, remember. So here it is. So D0 is again the pairwise distance matrix for cat0. D4 is the pairwise geodesic distance matrix for cat4. Run this. And again, I'm sort of taking a risk in the sense that I think the algorithm starts from a random point, as you can see over here, right? And then it iterates. So I do not guarantee how quickly this will converge. It may take quite some time. Okay. So this is for the first mesh, cat0 mesh. The Z are the n cross 3 matrices representing the points that we are obtaining, and the stopping criteria that I've used is how much does this solution or how much does the embedded points change every iteration. Okay, so as of now it's changing quite a lot. I think the threshold I've put is about 0.1. So you can imagine how long this will take. Okay. While we wait for this to converge, if you have any questions, please feel free to ask. This can take, I think, somewhere around 3 to 5 minutes. Again, this is not the cost function value. This is the amount by which your estimate of the solution changes. Okay? Do not sort of think that this should be monotonically decreasing. If we are unlucky, this may also sort of take a long time. Let's just hope it continues to go down monotonically. Threshold is set to be 0.1 as of now. of now it's going down reasonably well. So, and remember, this is the algorithm on the first mesh, so similar time can be expected for the second mesh as well. In fact, you can sort of start working on the assignment rather than just staring at these numbers. Once it is done, I take it. First mesh is done. The second mesh now. Let's hope it converges quickly. So close to, yes, it has converged. And let me first once again show you the original meshes. Remember, this is your cat4, this is your cat1. Using SpecOff, if we embed them using MDS in, again remember it, we are embedding it in a three-dimensional space. We get something. So the first one is for cat0. Something like this, and this is for cat4, right? So I think you should especially look at this picture, cat4. And if somebody knows how to get me to plot both these meshes on the same figure, then it would be worth looking at, in the sense that remember cat4 was quite a deformed version, but now they are sort of very similar, at least in a similar pose. Still, of course, some deformation. For example, you can see on the back, this looks fairly flat. It's here, it's still a little curved due to the deformation, but it's still trying to stretch it and bring both of these poses into a common, almost a common pose. After which you can, so basically you can see that they seem to be more rigid deformation of each other more than anything else. This and this. Okay, so that is sort of what the Smakoff algorithm does. After this, you can go ahead and do ICP, and can start with several initializations. So, in order to get better optima. All right, I hope it is clear what we are trying to do here. Any questions on this? Okay, Darshit has shared on the plot, which is this. Let me Right. Four. So, should this was the CAT4. It gets mapped to this. Let's now look at the output of your SMACOF algorithm for both machines. Right. You can see that it's more of a rigid problem now. We have eliminated at least a lot of the deformation that was there in CAT4. Of course, there is still this deformation here. You expect that to happen, right? Because there was some stretching. I said, let us ignore it, but of course, it's there. Okay, so basically, then do a rigid alignment. Right. So, yeah, this is what I had to demonstrate. I hope you can finish the implementation of rigid ICP and the MDS based, sorry, SVD based MDS. I'm available here for doubts. I would be happy if somebody is able to implement, maybe share your results. Any questions that you have, I'm willing to answer. Yesterday I had to spend a lot of time, more than an hour, just because of this difference in MATLAB and Python. And I'm not very sure, but I think the SVD that Python gives you does not return US and V. I think it returns US and V transpose. I had to put in more than an hour just to zero down to this difference between MATLAB and Python. Those of you who are familiar with MATLAB, please be careful. And of course, these algorithms, there's nothing special about Python here. Can as well implement them in MATLAB. And if you wish, I can also give you a quick overview to what is this optimization by majorization. Only if you wish, and hope you can first finish the implementation part, then we can discuss if required. So after finding R star and T star, you apply it, right? So as to align your source mesh and the target mesh re-indexed with the appropriate correspondence, right?
Yes, sir.
So then, I mean, you align it, but still there will be a misalignment, right? A little bit of error will be there in all points or some
Yeah.
points, whatever. You sort of square it and add it, that's your error. The next R star and T star that you obtain in the next iteration will also have some misalignment, but of course, the misalignment will reduce. So while this alignment error is reducing, your loop should continue. Once it increases, which means you have passed a minima, you should stop.
Okay, okay.
It's just one thing you need to be very careful with ICP. Remember all these transformations that you estimate here. That's a place where I think lot of students make mistake. Verified here. I've also written it with some emphasis in the notebook. All these transformations that you obtain, they have to be applied to the original source mesh. Okay, so it's not like after R1 T1 you apply R1 T1 to the source mesh, you have a new source mesh. Like let's name it S1. This R2 T2 has not to be applied to S1. It has to be applied only to the original source mesh S0. Okay, so just be careful here. All right.
Yes, sir. But sir, here source mesh is a head of cat, right?
Yes.
And the target mesh is cat. So what number of vertices are different.
Yes, but it's like you want to align source mesh to a corresponding part to the entire cat mesh, right?
Yes.
So when you compute C0, right, it will give you one corresponding point for every point in the head mesh.
Yes, yes.
So you should consider only those points from the entire cat mesh which have a correspondence to the head mesh.
Yes. Okay.
Okay?
Yes, yes, yes.
Okay. Yeah, in principle, ICP, whenever anybody looks at the scheme, it sort of feels very easy. It is, but there are these few points one has to be careful about. How many of you are trying? Darshil seems to be trying, surely. Anybody else who is trying?
Okay. So here, what I did, this is our J matrix, identity minus 1 1 transpose.
Right.
Okay. And then this is B matrix,
Okay.
and then I am getting the SVD, finding the SVD. So
Right.
US and V. Okay. And then this first three eigenvalues, this S contains first three eigenvalues.
Right.
And okay, and these are the first three eigenvectors and multiplied by this 3 cross 3 matrix. Okay, diagonal
Right.
matrix. So instead of I am getting this result of V4 mesh.
Can you replot that?
Yes, yes, yes. It is executing. Uh, Okay, so V0 EMB. So this in this way, the
Same.
like a plane, it is on a
Ah,
surface.
shouldn't get something like this.
And shape is 300
Yeah, that
3400.
should be fine. Scroll up.
Okay.
This at is something I'm not very familiar with. It's
At
just
the rate
matrix
is,
multiplication.
yes, it is just matrix multiplication.
Maybe try out printing
Mm,
this matrix J for a small value of n.
okay,
Again, so in principle, your code looks perfectly all right.
okay,
I
okay.
mean, I've done the same thing else. I just used np dot because I didn't know this at operator.
Yes, yes. NP dot matrix matmul like. Okay,
Let's try this. Take maybe n equals 4 and then try out
okay.
G.
Uh,
Some problem, right?
mm, uh,
Yeah, there's something wrong with G.
okay,
Because J times 1 has to be 0.
okay.
That will certainly not happen.
Uh, J times 1.
Vector 1,
Okay,
that has to be 0. It's not, you can clearly see here. The row, basically, the row sums should be 0. It's minus 3.
right.
So
Okay.
yeah, I don't know what this at is.
Uh,
Yes, this is fine. This is perfectly all right.
okay,
So then similarly, when you are using at somewhere else, it may have.
okay. Uh, st-
So that's what I don't understand about Python. I mean, there is np matmul, there is np dot, there is this at the rate. What is the difference? I
yes.
have no idea.
NP dot and
Sir,
NP
I
met.
think the star operator does element-wise multiplication, whereas the at the rate is the matrix multiplication that we do.
Yeah, but even
Yes.
this matrix multiplication is not giving the right result because 1 transpose, I mean, maybe you can just print what is 1 by n into 1 transpose using the at operator. You won't get this. What is this one? Okay, one star. Star is this element wise multiplication.
Yes.
One at the rate one dot transpose. What that gives, I don't know.
It gives a matrix multiplication of two vectors.
There is something wrong. Try it out.
Yes. 4.
Yes, hey, good. Ah, so this I think one is
Just row vector and this is the column vector.
no. I think when you just write np dot once, it is, so I think there is this another difference between Python and MATLAB. MATLAB by default, if you initialize a vector, it becomes an n by 1 matrix. That is not the case with Python.
Uh,
So you'll, this one, if you type what is its shape, right, you will see it's
4.
5
It's
comma nothing.
4 plus 1. Yes.
No, no. Just print one dot shape.
Okay. So then 4 comma nothing.
Exactly. I think so.
Yes.
See,
Yes.
so that is the problem.
Uh, okay.
See, so I think it's the same issue which has. I think what you should do is np dot once n comma one.
Right.